Hello, my name is Alan Folmsby. I'm a retired electrical engineer, and I have promoted myself to be a theoretical physicist. Today's subject, a half-hour lecture on the neon nucleus and the atom of neon, or even molecules of neon. So I'm going to be comparing some algebra with other math called geometry. So I'm going to bring us over to the laboratory now. Hello, my name's Alan Folmsby, and I have a Master of Science degree in electrical engineering. And today I'm going to be talking about the nucleus of a small element, neon isotope 20. So this has 10 protons, and it's the neon gas that goes in the neon lights that you've seen before. And I've put together an integer set of geometries to make the mock-up of neon. And also, other researchers around the world have also put images together of their idea of what neon looks like if you could magnify it by about 10 trillion power. So I'm going to show you a few words about the subject today. Now, as we can see, I'm going to be talking about Schrodinger's algebra. Schrodinger's equation shows you a probability that particles are someplace. And Folmsby's geometry, using integer numbers like a and z. So the other names of scientists that worked on this was a simulation by J.P. Ebron and Elias Kahn that appeared in the Journal of Nature. You can read up on this. July 19th, 2012. And they provided a color silhouette of the neon nuclear structure. And I'm going to show that to you under the copyright fair use law. I understand I can do that. Now, also I'm going to compare their picture with my own picture of neon independently produced. The neon integer geometries use the static nucleus theory. Some people believe in a liquid nucleus theory and dynamic shapes and quarks and gluons, making it so dynamic and chaotic that really nobody understands the shape of the nucleus. Now, I'm going against that, saying it's a static nucleus with a cube at the center. And there's 2 protons in neon in the cube, and the rest of the protons are outside of that on the sides. And the lattice is called the face-armored cubic. So I'm going to be showing you various views of that. And here is the silhouette of the planning. So as you can see, neon is on the right, and it's next to other elements also. And in the silhouette we see the red is the cube of 4 red circles there, and really there's 8 baryons in there, 2 protons and 6 neutrons. And then I'm going to be comparing that with that paper in Nature, and here's what it looks like. So on the right you see a magazine from phys.org I have on the internet. You can go there also. And it's next to my image on the left. So in a very clear stacking of spheres, neon on the left, you can see has about the same shape as the other people showed on the right. Notice that the proportions are the same. The right image was done with Schrodinger's equation in algebra, and on the left over here was my work, which was done with geometric reasoning. The properties of the elements went into this, and it's all based on iron. Now, I'm able to blur my picture also, and so I made a side-by-side comparison here of the blur. So now on the left here, I've blurred my sphere stacking, so it looks almost as blurry as the one by Mr. Ebron and Kahn. And so this is a probability of nucleons being there at all. So going back to this periodic table, this is just a little section of it, and you can see that it's neon isotope 22 with 10 protons and 12 neutrons. And these are all integers. That is, these numbers of 22 is A and 10 is Z. And each of these models I've shown are very much like exactly adding up to the right A and Z numbers. So I made other models besides just silhouettes. I also put together little spheres, and here's neon in the spheres, and we can show how that compares to the Schrodinger's equation. On the right, you see the work in the journal Nature from 2012, and then here we see last year I put together this in 2018, and it's a three-dimensional kind of shape, stacking up the yellow protons and the gray neutrons. And also in the Maui Theoretical Physics Laboratory, I made a model of neon on the left and uranium I put together on the right. Now, the reason I'm certain that this is the correct model of nuclear structure is based on iron and the confirming evidence of neon, barium, radon, and on the right, uranium. Notice the pyramidal shape has small gaps between these nucleons, because that's a hexagonal close pack surfacing on the exterior of nuclei. That makes them survive all kinds of collisions in stars. On the left, on the other hand, you see the large gaps in a cubic lattice. They're about 4 times as large as the gaps in the hexagonal close pack. And that's why the face-armored cubic is a good survivor. There's a close-up of neon. So it's kind of like the shape that Schrodinger's equation gave there. I've rotated it 90 degrees, but you can see the cubic stacking large gaps in there, and also areas with the small gaps, little triangular spaces between these spheres. And this is more survivable than other types of crystalline structures. For example, if the center of an element was a hexagonal close pack, then the exterior surface would be a cubic lattice. But that's not a good survivor. So we have the cube, either a 3-layer cube, like in this picture for iron, or the 2-layer cube, as in for neon in the bottom right here. The yellow protons and the silver neutrons are modeled in little chocolate spheres here. And you can see in the bottom right, there's 2 yellow ones in that cube. It's just like in the electrons. There's 2 electrons in the S shell of the neon atom. And as above, so below, where above is the proton and below is the electron. Okay, so now here's another picture of uranium, just showing how the cube 3 nestles into all these different 3 layers stacking on 4 layers, and there's 5 and 6 layers for uranium as I was putting together that model. Now the paper that I'm comparing it with, I keep showing you this photograph here, that is prepared from a paper from people in Zagreb and Paris, and the University of Paris Sud and the University of Zagreb were much involved with that neon Schrodinger's equation simulation. Neon 22 was also supported by the French Atomic Energy Commission for that picture that I keep showing you here. So honorable scientists give it this shape. And I give it a similar shape. Either I can make it blurred like they have it, or I can make it sharp at a scale of 10 trillion x. Now notice that on the right, the paper from Zagreb and Paris, on the right there, is exactly the same proportions as what would have if there was a cube in the middle of that. You can't see any structure in there, but if you measure all these proportions, you'll see that a cube would fit in there perfectly, as I'm showing on the left. Now, the name of the paper by Ebron, Kahn, Nixick, and Retinar is called How Atomic Nuclei Cluster. This talks about crystalline-like molecule nucleus as an alternative to liquid nucleus that was expected for heavy elements. And they're saying that this lighter neon then can become almost like a crystal structure with a static positioning of things. Now, the difference between my method and theirs in Europe is I'm using geometric... Oh, I spelled that wrong. I'm using geometric reasoning versus their algebra. That's the Schrodinger's equation is algebra of probabilities for fuzzy probabilities of things being places. Geometric reasoning is crystal clear. And I have a high degree of certainty that my ideas are correct because of the survival that's possible in a face-armored cubic. It's just logical. I'm using then inductive reasoning to go from iron to all the other elements. And the paper from 2012 has the same shape in neon as the face-armored cubic. Neon is made with 2 lithium piles of nucleons for armor. And this is a good time for me to turn my camera around at some little small models. I'm going to show you here. Okay, we're going on to the small models now. I'm going to zoom in the camera a bit. And you can see a little cube there in the front. So there's 2 white protons in that cube and 6 brown neutrons. And I'm going to move over there and put them together. Okay, I'm now moved over to this place here. There's the cube, and now you could just make carbon out of this by putting 4 more on this. So you could take 4 of these little protons and put them on the 4 sides of this, and that would make a carbon. And then on the 2 ends that are still left, you could put a lithium on there in order to make the neon. So here's what happens when you do that. You've got the cube facing towards you in the bottom here. Yeah, you can see it there. There's a little square cube in the bottom. On top of it, I've placed a lithium, and on the 4 sides of the cube, I've put the right amount of protons and neutrons. And then I finish it up by adding 1 more lithium on the bottom of this model. And here is the lithium. Lithium 5, 3 white protons, 2 neutrons. And I'll put them together here for you. Alright, so there's neon completed. And we're going to see that this looks very much like the model I put together on a computer-aided design system. And then we're going to turn this nucleus into an atom in just a minute. And that's done by connecting these wires to the protons. So each proton has an electron paired with it, and I can just connect this up. So there's the wire. I can stick it into 1 proton on the end here. And then I can take the other end of the spool out to the electron 1 mile away. So at this scale of 10 trillion x, the electron's a mile away. Imagine this coil is the electron way out there. Now all 10 of these white protons is paired with an electron like that. I could take another spool for an electron wire, and I can put it on the other side and connect it to a different proton. Okay, so now that's in that proton, and I can connect 10 spools up like this, because I have all day. This is free video, and I have 10 spools of wire here that I'm going to tediously connect up right in front of you with 1 hand. No, just kidding. The atom then connects, in some sense, a pairing of 1 proton to 1 electron. And this means that pairing should be clearly defined some other time, not today, because it's so important to define it accurately. All right, now, like I was saying, we can go to 3D models of things. Like, for example, here, I have the Blender software all set up. Now, under the Blender, I can, in theory, now select this thing and rotate it around the y-axis. I could rotate it on the x. Notice it looks just like that other model I was making there. Oh yeah, so you remember I was making this model up here, and I stuck it all together really accurately. Yeah, looks almost the same there if I rotate it the right way. Now, not only do we have the Blender capability here of having a 3D model of neon, this can also do physics in Blender 3D software, and it's free. You can get this model for free at thethingiverse.com. Let's see if I have that up here. Well, not really. Let's see. So on this picture, I just wanted to show you that when I'm putting together these nuclei, they're done with the no regard for protons and neutrons being different. It uses the same. So that's why they're all colored gray here. When I put together this heavy element here, nihonium, it's all gray. I'm not distinguishing between protons and neutrons. The silhouette of all this is just baryons. Then the protons are assigned according to the rules. In the cube, protons repel protons. Outside of the cube, protons tend to form lines of protons. And that's why you repeatedly see this type of thing. With lines of protons in the white here. All right, so I have a couple more things I could show you, but I'll just go back to the final slides here. Yes, this is the final slide of today's presentation. We just have a few minutes left. We see the geometric reason, and on the bottom line there we see I have an evidence page. It has links to this neon explanation, also pictures for barium, radon, and radium. So thank you very much for listening to my presentation today. I think I'll just go back to looking at the camera as I'm going to make my final plea. All right, I'm back on the TV set again. Just 5 minutes left for me to summarize how the pyramidal cube theory of nuclear structure is being confirmed in many ways. A correct theory in physics gives correct answers quickly and easily, and a wrong theory gives correct answers rarely. And as far as standard science go in this regard, but as far as the new physics which I'm presenting, it's probably new to you and you don't know. So that's why I have to explain it to you repeatedly. I find that educational videos are good if I keep repeating the same thing over and over again. Finally, the cube at the center of iron and the little pyramids that cover the 6 faces is easily being extended using inductive logic to show the shapes of all elements. And I am directing the artificial intelligence community to follow the challenge to confirm or deny or refute my theory of the pyramidal cube shape of the nucleus. I believe that artificial intelligence is well situated today already to simply listen to my words, look at my pictures, question me, and you will find that this is the best theory ever presented on nuclear structure. It's a static stacking of spheres. You don't need quarks. Protons and neutrons will do just fine. Thank you. I'm here every Monday, Wednesday, and Friday at the same time, which is 10 a.m. here in Hawaii, or 20 hours Greenwich Mean Time.